and I'll give some examples of like actual CBC design in CBC Casper, and some of the, stuff that happens. It's give you kind of a taste of the methodology and the kind of approach that we have that kind of sets apart CBC Casper from, other consistent protocol research. And finally, the last bit of my talk, I'll remind you all of where the resources are, show you some new resources, and make some announcements. So, let's talk about design methods in CBC Casper. The number one kind of design methodology in CBC Casper is the correct by construction design, protocol design methodology. The idea with correct by construction is that the process by which you decide what program you write should guarantee that that program has the properties that you want. The very process that you use to specify the protocol should guarantee that the protocol has the properties that you want. So somehow the way you decide what formats to use or what the protocol is in terms of the data and the behavior, that happens somehow. Definitions don't come out of nowhere. And there's a process by which stuff gets defined, and it's called, the process is called correct by construction. If, if the process that you use to define the thing somehow guarantees that the definition that comes out is correct. And this is kind of as opposed to the trial and error approach, where you will try something and then analyze it, and then it might work, it might not, or maybe get lucky, and if not, then maybe learn something and just keep trying until maybe you'll find something. So this is a very different approach, right? Because instead of, we never really have the trial and error, we just have a lot of time defining stuff, and then once the definition pops out, it's correct by construction, so there's no error, but in some way, it takes us a lot longer to come out with a full definition. But when it pops out, we know it's correct by construction. And we don't worry at all about mistakes in the specification in the same way. So there's two basically kinds of correct by construction software design I'm kind of aware of. One of them is, you define a proof, maybe a type system and some proofs over a broad class of protocols or broad class of programs, and then you, in your design process, choose your protocol to be part of that set, so that when you choose it that it's going to satisfy the theorem that is inhabited by this much broader set of protocols. So if we have a family of protocols, they all satisfy a theorem, and we pick protocols or construct them in a way to guarantee that it's part of the family, then we can, in a correct by construction way, get a protocol that has that property that the theorem shows for the family. And then the other kind of approach is that the protocols are specified in a way that actually generates a proof of their correctness. So you generate the protocol and the proof, a new proof for every protocol. And then don't do any of that. It sounds hard. I've heard people doing it in programming languages and compilers, but that hasn't showed up for me yet. So what I do here is basically we define large families of protocols and we prove things about them, and then we choose specific protocols out of them, which will, by virtue of being in those families, have these properties. So now we're going to switch over to this very related topic, but going off into the math deep end. So domain theory is a field of mathematics that studies it studies the semantics of programming languages, but the reason why it's super interesting to me and to just why it's really useful for understanding the correct by construction process is because it provides us a language for talking about partial definitions, incomplete definitions, partial protocol specifications, and we can understand what it means to have a process of defining something, as opposed to just having something that's outright fully defined, as you might have in set theory. So you should think of domain theory as something that arose out of people's feelings that set theory was inadequate for dealing with programs and the semantics of programs, especially recursive programs and lazy evaluation. I'm not an expert in domain theory, but there are some things that I've learned from domain theory that I find super useful for thinking about a bunch of stuff, including correct by construction protocol design. So there's a really, kind of core notation in domain theory to use this, and to define this thing called undefined. So this bottom notation means undefined. And it's like defined to be the most undefined thing. It is the most undefined thing in this partial order of definedness. It's like, if I say nothing about my protocol, then like I've left it completely undefined, and somehow it's like the most undefined that I could leave it. And as soon as I say stuff, it becomes more defined. And we can talk about and reason formally about this order of definedness and this process of defining stuff, and having at certain stages a partial definition, and then getting in more and more defined protocols. So if A is a definition that can be reached from a definition B by replacing an undefined term in B with something that's defined or something else, then A is more defined than B. So basically, like if I have a definition, it's got some undefined term in it, and I can replace it to get some other definition, then that other definition is more defined than this like initial definition. So I'm going to give some examples. So here we go. Bottom times bottom is more defined than bottom, because you can replace bottom with bottom times bottom, and therefore you can define something which is completely undefined bottom to be this thing bottom times bottom, which is still not totally defined, but it's more defined than just bottom. Bottom times empty set is more defined than bottom times bottom, because you can replace bottom with empty set and get from bottom times bottom to bottom times empty set. What about empty set times bottom versus bottom bottom? Well, you replace the first bottom with an empty set, and so the thing on the left is more defined than the thing on the right. But the next example is a little trickier, because it's not more defined than the thing on the left. Sorry. The empty set times bottom is not more defined than empty set times bottom times empty set, because you can't replace the bottom to get empty set times bottom, because there's already an empty set in that position. So, basically what we're doing is replacing the bottoms on the right to see if we can get the thing on the left. And if we can't, then it's not more defined then. And if we can, then it is more defined then. So at the end of the day, what we kind of get is this picture, this partial order of the definedness of these terms. So like bottom is the most undefined. Bottom times bottom is a little more defined. These two terms, the left and right, they're not more defined than each other, even though they have a term that is in common, a term that both of them can define. A term that inhabits both of these partial definitions. And so kind of, what we do in the correct by construction process is we move from less defined protocol specifications to more defined protocol specifications. We have a kind of process of, we say something about the protocol, then we prove things about the protocol, so that later when we continue to define the protocol, the things that we proved continue to hold, because all of the later definitions are just a refinement of the previous definition. So the kind of theorems that we have for less defined versions of the protocol spec are going to hold for more defined versions of the spec. And this kind of starts to make you feel why we have like this correct by construction protocol design, because at some point we're going to have a partial spec and some proofs, and then there's no way for us to define that spec more that will kill those proofs. So basically, like our kind of strategy is to like deliberately give partial specifications and prove things about partial specifications, so that we can have a lot of flexibility in our iteration and design, because we can continue to define from that point in many different directions without having to worry and go back about verifying and changing proofs that because of the change in the protocol. So like a lot of the time when you have a protocol, when you make a change, you're gonna have to like change the proofs that you have about the protocol. But if you instead had some partial definition of the protocol that you had some proofs from, which you could change, and you could make your change to your protocol by just continuing to define the protocol, just like in a different way from before, then you can not have this additional proof obligation because you just have proven it for a much broader class of things, which are kind of the things that inhabit this less well-specified definition of the protocol. So let's, I think we can get a lot of flexibility in design, and because of this approach. And so here's some actual partial order of definedness in some definitions that we have in the CBC Casper world. So we have this minimal CBC Casper family of protocols, which is the specification that's the easiest to understand, the smallest, the fewest parts, and we define terms in that specification to define the binary consensus protocol, the blockchain consensus protocol, and other consensus protocols that you've seen if you've watched me present on CBC Casper over the years. And so all of these protocols, these three protocols, the binary consensus protocol, the integer, and the friendly ghost, they're all more defined than the minimal CBC Casper specification, and they all satisfy the same proof as the minimal CBC Casper spec. And these all, therefore, we kind of benefit from that proof, and we don't need to look back much when we're defining forward from this minimal CBC Casper family. We don't need to look back and ask about whether that proof will continue to be satisfied. But this family of protocols actually has a full node condition. It requires that all the messages, all the nodes, processes, all the justifications of all the messages. And so that's actually not super useful, for example, for sharding. And so we don't actually want to have to define sharding as a further definition of this specification because it requires this full node condition. And so actually what we do instead is we have this other spec, which is this light client spec, which, where clients don't need to have resolve all the pointers and all their messages. And so we define the sharded blockchain consensus protocol spec as an instance of this light client CBC family of protocols, which all satisfy the same consensus safety proof. And actually there's a more abstract family of protocols, which is considerably harder to communicate than the minimal one, but which is less defined than both the light client protocol and the minimal CBC Casper protocol. And so if we, with this kind of setup, what this does is it gives us a little roadmap of starting from where, what is defined and what properties do you have, and if you go downstream from there and continue to find stuff, what do you get to benefit from? And so it can be really, I think this kind of notion of the order of definedness and of progressively giving more and more defined protocol specifications is very, 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 very much what we're doing in correct by construction protocol design, because we're engaged in the process of defining something, and at the start we don't have a full definition. But we want to get to a point where we do have a definition that satisfies certain properties. And we want to know that the process that which we follow will guarantee that we have those properties. And so, we try to have this kind of a disciplined approach for getting them one step at a time in a way where we don't really have to look back. So, but it's not always as straightforward. Sometimes we have alternative choices of how exactly to define stuff, and even to get the same goal. So it's, I painted a pretty simple picture, but the reality is more complex. For example, for validator rotation, the easy thing to do in terms of the protocol specification and the proof obligations is to just launch lots of instances of these protocols that have new validator sets. And that really can work in some cases. But there are also cases where we want to define protocols that do validator rotation in a way that is outside of the minimal CBC Casper framework. And whenever we do this kind of design that's outside of the framework, we create new proof obligations. And so we sometimes have to have a choice between, do we design things in a way to take advantage of existing proofs, or do we come up with a new system or a broader family that have other proofs? And it's tricky because on the one hand we want to benefit from all the proofs we already have and don't want to make any new ones. On the other hand, when we can generalize stuff, sometimes we can generalize it a bit and not as much as we'd like. And so if I come up with a more general family of protocols for doing validator rotation, for example, like I haven't come up with one that really does everything I want. And so there's definitely, it definitely isn't as simple as like, you know, define as you go and everything will be fine. There's real choices that we need to make and like in the design process. So one of the decisions we made, for example, is that validator strategies are not part of the specification. Like the core, like the, you know, the core partial spec is only for clients. It's like not the spec for miners or for people who make messages. It's for people who receive them. And the reason why we did this is because it's like kind of it separates out the parts of the protocol in a way that allows us to tackle them separately, and we can, like, independent of when validators make messages or of how validators make messages, show consensus safety. So we have this big part of the protocol of like when do nodes make messages, which is not defined in the core spec, which both seems weird because you would expect that to be part of the consensus protocol, but also is really nice because there's no way that that term could be defined in a way that disrupts the proofs in the for the like client protocol. And so validator strategies are not in the core partial protocol spec, and that was like one of the decisions we made, and I definitely don't regret it at all. We have a bunch of design decisions that were motivated by economic thinking, but also at the same time we leave incentives undefined until very late in the game, because the incentives have to respond to the actual states of the protocol and the actual the consensus protocol itself, and so you can't actually define the incentives until the consensus protocol is defined. And so although we do a lot of thinking, economic thinking up front, and we come up with a lot of distributed systems properties that we want based on the economic thinking, the definition of the incentives is left for later. So, you know, we have the fault tolerance threshold is not specified in the protocol. It's like a decision we made, like very, like, you know, like not an arbitrary decision, and it was motivated by like the design requirements that we have. And we have, and this is like an area where it's not in the core reference spec, but we have a proof for how nodes would use it with different fault tolerance thresholds. And so we can, without changing the core spec very much, give proofs for a new kind of use of the protocol. So, you know, more kind of weird proof tactics around, you know, using multiple instances of this, like correct by construction, core protocol, partial spec. You know, we have preventing DOS will require, like, you know, that we bound the amount of work required to process a message, and that people have throttling for the amount of messages that they can receive. And so that requires a new constraint on consensus messages. It requires new strategies for the validators. None of this stuff is part of the core protocol spec. None of it is part of the minimal, you know, core piece of the, like, you know, of like the start of the correct by construction process. And all of that is kind of very deliberate because the idea is that we can define this stuff later, and it's more than fine because we didn't screw it up by defining it earlier. So the other kind of you know, really cool thing about the correct by construction approach is the fact that you can iterate actually quite quickly without having to, because you don't have to reason about much of the protocol when you make changes, because you literally could not define it in a way that screws it up. And so I'm going to show you some of the progress we've made in the last little few months on some of the sharding stuff. So this is what came out of the ETH Berlin hackathon. We came up with like a pair of shards, one of which kind of follows the other one. It's very similar to the traditional CBC Casper consensus protocol in the sense that, like, it's, you know, it's really implemented at, like, completely as just a definition, a further definition of that protocol by giving the consensus values and the estimators to the validators and their weights and the fault tolerance threshold. So we did this binary, so we did this two shard system. And one thing that we kind of have been wanting to do for a while that finally kind of got to implementing is, in just like a few months, like a really short order, is shard rotation. So like here what we see is two shards that are changing position. One of them is the root at first, and then it changes, and then the other one is the root, and then it changes again, and the other one is the root. So the purple blocks there are root blocks, the yellow blocks are child blocks, and the roles of these shards in the hierarchical consensus are changing. And this does not require that we reason about consensus safety at all, because the correct by construction process kind of guarantees that with no thought, because it's kind of upstream from our definition process. And so relatively little work compared to normally working consensus protocols. We define this actually relatively complex consensus protocol that like this comes to consensus on, the state of two shards with blocks that have like two different positions and have like a relatively complicated fork choice rule. And here's like the kind of next kind of conclusion of that is like, oh look, when we have two shards that can send messages, we can do routing. We can move shards around in two positions, we can move shards around even more. And then we have this, pretty cool sharding solution where we have messages being routed around cross shards, like the atomicity property that if your route isn't fully completed, then the block that started that route will be orphaned. So we have like, a really kind of strong ability to iterate very quickly because of the correct by construction approach, because we don't need to look back at the previous guarantees. We're not at risk of disrupting them. And so, I'll walk through this again. So what's going to happen here is first the root shard was initially 0, now it's switching to 1. These messages are being routed from shards 6 to 3 and back. Shard 0 and 1 switched from 0, 1 to like 1, 0 and then back. And then shard 3 became a child of shard 4, even though it was previously a sibling. And then messages start to get routed through shard 4 after that swap. So it's really kind of quite complicated. We have like routing tables and they're updating, but we really didn't need to think about consensus protocols almost at all while specifying this thing. So, we have... So we have like a methodology that lets us define consensus protocols. We've defined a large number of consensus protocols, or partially defined a large number of consensus protocols. And, and we iterate while creating minimal proof obligations, and we are able to mix and match kind of a lot. And, so I recommend that you try out, correct by construction. And we, sorry, I'm looking at the wrong slide here, so I got ahead of myself. That was the next slide. So we basically really rely on these partial specifications, and the fact that it's not defined yet is actually a huge asset for us. The fact that we leave things undefined until the latest possible moment means that we have as much flexibility as possible to iterate without disrupting our previous proofs. So I already said all this. Yes, it's great. Try it. Correct by construction protocol design. It's awesome. So now let's moving to the kind of announcement section of the talk. So that was pretty much all of the content. So we have a bunch of announcements of people contributing to CBC Casper research. This is Rob Hamrock from True Level built generative testing for CBC Casper protocols. Let's see if I can. And with this, spoiler alert. So what this kind of shows here is the red dots are members of a clique, which are validators who see each other agree in a way that they are actually finalizing that block, the blue one down there. And this is something related to the way that finality works in Casper. And here we see multiple views of the protocol from point of view of 4 different validators until one of them finds a decision on this block, namely finalizing, this blue block. And the green dots are the messages from the validator whose view we see, and the red dots are the clique, which is like a group of validators who sees each other agree in a certain way that corresponds to a consensus signature that is like a decision. So that's pretty cool stuff. I mentioned the sharding proof of concept. We've been working on this with like a significant rotating group of people since the ETH Berlin hackathon. Actually, before that, at the Ethereum IC3 workshop, we worked on the specification. Especially want to give a shout out to Alex Skidanoff, who in the last week and also during the ETH San Francisco hackathon put in heroic efforts to get the routing working and the shard swapping. I mean, he's the first person to prototype the cross-shard message routing. I'm a bit jealous. You should check out this GitHub repo and see if you like it. And there's still loads of bugs, but it's definitely interesting. Aditya, who is probably somewhere here, has announced that he's implementing a sharding client with Ethereum blocks and very Ethereum sharding client. And he has a GitHub repo and a Twitter handle. You should follow him for his work. This is an exciting one. We kind of released the draft, or are going to release a draft. I wrote these slides. I thought we'd have it released by now, but we're going to release a draft today. Oh wait, it is released. My bad. GitHub.com/CBC-Casper. And you can download a new specification of the minimal CBC Casper protocol states that is, extremely rigorous and pedantic, with extremely rigorous and pedantic proof of the consensus safety result and example protocols, including the friendly ghost, the finality gadget, sharding with fixed hierarchy. And I'd like to thank my co-authors, Nate Rush, Aditya, and Georgios. And they're all here. You can probably recognize them from their faces. Aditya's face was on the previous slide. Finally, don't forget about the prototype and the wiki at Ethereum/CBC-Casper. Those are good resources if you want to dip your toes and check it out. We're totally looking for help of all kinds, and we're getting better and better at helping you help us as the documentation and definitions and stuff have laid themselves out in a way where you can come in and contribute in a way where it's really clear how it interfaces with everyone else's work, and where you won't be wasting your time and you will be helping. Reach out, and thanks so much for listening.